Okay, so we have the mass of the bullet, velocity of the bullet, and then we took the mass of the rifle and velocity of the rifle and we subtracted that to the other side, and we're trying to solve for that velocity of the bullet. So I'm going to divide by the mass of the bullet. Okay, so this is what we end up with here. We're saying, well, the velocity of the bullet is this ratio between the rifle and the bullet multiplied by the velocity of that rifle. And so the rifle is going to be much bigger than the bullet, and so we get this big velocity of the bullet. Now, what if we went the other way? Well, if we're trying to find the velocity of the rifle, so we'd subtract that over, right? And then we would divide by the mass of the rifle. So that would be velocity of the rifle would equal negative mass of the bullet divided by mass of the rifle multiplied by the velocity of that bullet. And this ratio is much smaller because this is such a small mass compared to such a big mass, right? And so what we see going on here is that this is going to be this small fraction multiplied by something is going to be small. So we have a small velocity of the rifle recoiling, going back, but we have a big velocity of the bullet because that ratio, the rifle, is so much bigger than the bullet, and that big number multiplied by something will give us a big number. Okay, so that's where we can compare that velocity of the bullet and the rifle. That's how recoil works. Okay, example number 8. An astronaut is at rest in space during an EVA. In order to return to the spacecraft, the astronaut fires a thruster that expels 35 grams of gas at 875 meters per second. The combined mass of the astronaut and thruster are 84 kilograms. How fast and in what direction is the astronaut moving after firing the pistol? Okay, so the combined mass of the astronaut and the thruster is 84 kilograms. And I think that's meaning before it expels the 35 grams of gas. Okay, so let's think of what's happening here. We initially have everything all together, right? We have our astronaut with the thruster, and it's full of the gas there, okay? So this is the initial, everything's at rest. So mass of this combined initial object is going to be 84 kilograms, and then the velocity initial of this object is 0. Okay. Then the astronaut expels the gas, right? And so now we have our astronaut with the expelled gas. He's now traveling this way. The gas is traveling that way. And now the mass of this object, what are we going to call this? We'll call it, so this will be the mass of the astronaut and the gas, okay? And then this will be the mass of just our astronaut. And so that would be mindful that this is grams, okay? So in kilograms, that would be 0.035 kilograms. So I'm going to take 84 minus the 0.035. So that'd be 83.965 kilograms. And then the mass of the gas is 0.035 kilograms. and the velocity final of the astronaut. That's what we're looking for, right? How fast and in what direction is the astronaut moving? And then we know that the velocity final of the gas is a positive, because we're calling this a positive direction, 875 meters per second. Okay. The sum of the momentums initial are going to equal the sum of the momentums final. And initially we just have one object. We have momentum initial of this astronaut and gas object all together. And that's going to equal the final. This is an explosion where we started with as one object and we broke up into two or more. Okay? So then the momentum final, well, we have two objects, so that'd be the momentum final of the astronaut plus the momentum final of the gas. And we know what momentums are. Momentum is mass times by velocity. And that's going to equal mass of the astronaut times by velocity final of the astronaut. And then mass of the gas, velocity final of the gas. This is equal to 0, right? These initial are not moving, and anything multiplied by 0 is 0, so that whole thing is 0. And then we're solving for this. So if we have anything added or subtracted, we should move that first. So we're going to subtract that to the other side. So we'll have negative mass of the gas multiplied by velocity final of the gas. And that will equal mass of the astronaut multiplied by velocity final of the astronaut. That's what I'm solving for, so I'll divide it, the mass of the astronaut. Alright, so we have a negative, top of our fraction, mass of the gas multiplied by the velocity of the gas divided by the mass of the astronaut so the final velocity would be, what are we looking at? 3 sig figs, 2 sig figs, 2. So we'll go with negative 0.36 meters per second. Okay, let's ask ourselves, is this reasonable? First, did you expect a negative velocity? Ideally, hopefully, right? Because if the gas is moving this way, then the astronaut would be moving that way, and we're calling this positive, so that must be negative, okay? And we didn't expect him to be going anywhere close to this because the astronaut is so much more massive than the gas, okay? The momentums, what we started with is what we ended with, okay? All right, that seems reasonable. So, summary. Elastic collisions, inelastic collisions, and explosions. Well, we know that whatever we start with is what we end with. And typically when we're elastic, we are separate beings when we start and we're separate beings when we end, right? That we have momentum of 1 initial plus momentum of 2 initial will equal momentum of 1 final plus momentum of 2 final. Okay? And with an inelastic, we start as 2 separate and then we come together. So that would be momentum of 1 initial plus momentum of 2 initial. But then at the end, we're one object, so that would be momentum of this combined 1, 2 object. Okay? And then with an explosion, if we start off as 1 and then we break up in different components, it's the exact opposite of this. We have momentum of this combined object initial will equal momentum of 1 final plus momentum of 2 final. Alright guys, so that's it for learning target number 3. So make sure you get that concept check done. Let me know if you have any questions and get working on that assignment.